This is the very first television ever invented, and inside it sits a spinning disc. The disc has 30 tiny holes arranged in a spiral pattern. As the disc spins, those holes pass one by one across this little window. When the disc rotates fast enough, what you actually see is a series of thin lines flashing past. When light enters the window and passes through a hole, it hits a photoelectric tube behind it. The photoelectric tube is built from selenium, which generates electricity when exposed to light. It measures the brightness of that light and converts it into an electrical signal. The signal is then sent to a display through radio waves or telephone lines. Once it reaches the display, the signal gets amplified and fed into a light bulb. The bulb constantly changes its brightness based on the incoming signal. Behind that bulb, there is another spinning disc. As this disc spins, light of varying brightness hits the screen behind the display. Of course, a single dot can't form a complete image on its own, but once you spin the disc fast enough, a continuous flow of light and shadow appears. It covers the entire screen, forming one complete picture. The resolution was terrible, running at only 5 frames per second. It stuttered badly, but it was the crucial first step from 0 to 1. The problem was that this TV could only show black and white. So to bring in color, the inventor, John Logie Baird, divided the holes on the disc into 3 groups. Each group was fitted with a red, green, or blue filter. Now when the disc spins, what you see is 3 sets of colored lines passing through in sequence. The same setup applied to the display, with its disc also split into red, green, and blue groups. When a red hole rotates into place, the red signal triggers the bulb to light up. The same goes for green and blue, where each color signal controls the bulb in turn. As a result, the screen displays red, green, and blue one after another. Once the speed gets high enough, all 3 colors sweep across in rapid succession. The human brain can only hold onto each image for a split second. So what you actually see is a full-color image, blended from red, green, and blue. In 1928, Baird unveiled this color television at a public demonstration. The audience was blown away, but this kind of TV still depended on mechanical parts to operate. That made it pretty limited in practical use. So how did scientists push past this barrier? Back in 1857, 2 German scientists ran a now famous experiment. They placed 2 metal electrodes inside a glass tube. Then they pumped out all the air. After that, they sent an electric current through the electrodes. To their surprise, the entire glass tube began to glow, and the more air they pumped out of the tube, the more concentrated the light became. Then they grabbed a magnet, and the beam of light actually shifted along with it. After digging deeper, they found it was because the current was sending electrons flying out of the cathode. When those electrons slammed into the end of the tube, they released energy as light. Another German scientist, Ferdinand Braun, took that concept and ran with it. He built the world's first cathode ray tube, or CRT. On the glass of the tube, he placed 1 horizontal and 1 vertical electromagnet. These electromagnets could precisely steer the electron beam inside the vacuum tube. That made it possible to draw exact patterns on the screen. It could also change the brightness of each line based on the electrical signal. The result was a much sharper image. Fast forward to 1931. American scientist Vladimir Zworykin used the cathode ray tube to invent the iconoscope, the first electronic image pickup tube. It basically worked like a video camera. Light enters through the lens, which then focuses the beam onto a photoelectric target plate inside the system. The back of the plate is coated with a thin silver film. The front side holds thousands of tiny light-sensitive particles. When light coming through the lens hits the target plate, those particles release electrons, and they lose their charge. The more light that hits them, the more electrons they release. This creates areas of varying brightness across the plate. The dark areas hold onto their charge, while the bright areas have lost it. Then an electron gun inside the tube scans the image line by line. When the electron beam strikes a charged area, the beam bounces back. It then crashes into a detector inside the tube. The detector converts the light signal into an electrical signal. These signals can then be sent out for further processing. Building on this electronic image tube technology, the CRT television was finally born. That's the chunky old set folks fondly call the big butt TV. If you pop off the back cover, you'll discover that the bulky rear is actually the picture tube. At this spot on the picture tube, there is an electromagnet. Mounted on the electromagnet is an electron gun. It fires electrons and serves as the cathode. On the opposite end is the anode. The entire picture tube is painted black to stop unwanted reflections. The fluorescent screen of the tube is coated with phosphor powder. When the electron beam strikes the phosphor, it lights up. But the screen is made up of countless tiny pixels. A single electron gun can only fire 1 dot at a time, so only 1 point on the screen lights up at any moment. The catch is that a single dot can't actually form an image. The solution is the same idea we saw earlier, and that's speed. The electron gun scans so fast that we can't possibly track where the dot actually is. It can hit countless positions in a single second. It even shifts position within microseconds. To our eyes, it looks as if the dots are appearing in multiple places at once. As long as the refresh rate is fast enough, we see a full TV picture on the screen. But people weren't satisfied with that, because this TV could only show black and white. The question was how to add color and the American company RCA cracked the problem. They sent the incoming light through a special prism filter to split it into red, green, and blue. Each color was then routed to its own dedicated image pickup tube. Each tube produced its own separate signal for that color. On the TV side, those signals were fed into 3 independent CRT displays. Then a set of lenses recombined the images back into one picture on the screen. The problem was that it required 3 CRT displays that tripled the price of the TV overnight. On top of that, it broadcast 3 separate color signals that made it completely incompatible with existing black and white TVs. To solve these issues, RCA came up with the idea of packing 3 electron guns inside a single CRT. All 3 would scan the screen at the same time. The screen itself got a special treatment. And if you zoom in, you'll see that it's coated with tons of phosphor dots. These phosphors come in groups of 3, red, green, and blue, forming 1 pixel. They cover the entire screen. When an electron beam strikes a group of phosphors, they glow at a brightness based on the beam's intensity. This way, the TV can control the color value of every single pixel. When you step back and view it from a distance, the colors blend together. That's how a full color image is formed. But there's still a catch. Pixels are incredibly small. How do you make the electron beam hit each one with perfect accuracy? The fix was surprisingly simple. Engineers added a shadow mask right behind the screen. The mask has tiny holes that line up exactly with the pixels. When the beam comes through, it can only pass through these holes. That lets it hit the phosphor dots with pinpoint precision. Because the picture tube scans so fast, our eyes can't tell what's happening. So what we see is a full color image blended from red, green, and blue to keep things compatible with black and white TVs. Engineers gave the signal a special treatment. Before transmission, the red, green, and blue signals were combined into a single brightness signal. Then an algorithm processed the color signals to produce 2 separate signals. The I signal mainly covers the orange and blue tones. The Q signal mainly covers the green and purple tones. As the signals shift, the color values shift right along with them. These 2 signals are 90 degrees out of phase with each other. When combined, they form a single chrominance signal. That signal is then modulated onto the brightness signal based on its frequency. For black and white TVs, the chrominance signal just gets stripped out, and the picture displays fine. For color TVs, the brightness signal is stripped out instead, leaving only the chrominance signal. But the chrominance signal has to be decoded before it can be used. At the start of each transmitted signal, there is a short burst of a sine wave. The TV compares the chrominance signal against this sine wave and looks for the differences. That's how it extracts the I signal. Then it shifts the chrominance signal by 90 degrees and runs the comparison again. That's how it pulls out the Q signal. Since the I and Q signals were generated using known formulas, running the math in reverse gives us back the red, green, and blue color values. Those signals then get sent to each electron gun in the TV, and finally the picture shows up on the screen. These days, CRT televisions have been pushed aside by LCD and LED TVs. But for those of us who grew up in the 80s and 90s, they hold on to those fuzzy, warm memories of childhood light and shadow.